right, so the homework. So the question is, if we start at the top, how well can we do here? So we start up here, we have 64 convolutions that are 3 by 3. How deep are they? Here. What? It's 3 because? No. The depth of the input is 3. Exactly. So the depth of the input has to match the depth of the convolution so that the convolution can work. So the depth of the input is 3. And now, do we know the output size? We do not know the output size. Because what does the output size depend on? Padding and stride. And do we know the padding and stride? We do not. All we know is that it's the same for all the convolutions. So we've got to work our way backwards, right? Because I gave you the final size here, right? This max pool was a 7 by, if it's 7 by, what's the next thing? 7 by, how do we know it's 512? Because there are 512 convolutions before. Okay? So that's that same idea here. All right. So if this is 7 by 7, and the max pool drops us by a factor of 2 in each direction, the previous is 14 by 14, and we know the next max pool is going to take us 28 by 28, the next 56 is 56, the next 112, 112, and the final one, 224 by 224, which means each convolution is not changing the size. Therefore, we can determine the padding of a convolution is half padding, and if we talk about how many units it is, it's 1, right? It's 1 pixel padding. But half padding is a good description, and the stride is 1. Yeah, standard stride. We just go one by one. All right. The sizes, I believe everyone got right. I've graded about 20 of them, okay, so far. So, were there any questions on the sizes, though? Either the sizes of the convolutions, the sizes of the ReLUs, or the max pools, or the output sizes?
Can you explain where you got the stride of 1 from?
Yes. So, if we've got a k by k coming in, and we have a convolution that we know is a 3 by 3, and we want it to come out as a k by k, then we're forced to do 1 stride. If we did a 2 stride, we would be approximately reducing the size by 2. Okay, does that help? Okay. And actually, you almost rarely see any stride other than 1 for convolutions. For max pools, it's normally 2, because you've got a 2 by 2 pool. All right, the weights. Let's start out with simple weights. What are the weights of the ReLUs? 0. How do you know that? It's on there. Exactly. And now we could just double check and see, is that a reasonable thing that I said? And it is, right? ReLU, we just look at a pixel, or look at a value, an input value, and either leave it alone or make it 0. There's no weight we're learning on how to do that. We don't need any extra information besides the input for that. Does that make sense? Okay. What about max pool? With the weight of max pools. Also 0, because there's no extra information needed, right? If we have, let's say, z equals xw plus b, we have this extra information, the w and b that we're using to compute the z. But if we computed a from g to z, there's no learning here that's happening. So if we do a max pool, and we take our 4x4 to a 1x1, pick the maximum one, put it in there. Nothing to learn, no weight. Okay, so the weights of all the max pools are 0. Does that mean the number of inputs is 0? No. The number of inputs, I mean, we have a particular input size, right? This tensor of h times w times d. And the output is going to be half h times half w times d. But there's no weights. Does that make sense? Okay. As opposed to, let's say, the softmax. Right, for the softmax layer, what weights do we have? We also have 0, but this tripped up a lot of people. Right, we've got 1,000 outputs coming out of the fully connected layer. And then we feed that into a softmax. What does the softmax do? It takes, right, 1,000 outputs, and the first thing it does to them is, anyone for a softmax? Takes e to the x for all these, and then divides by the sum of the e to the x's, determinant of probability. But there's nothing we need to do here weight-wise. We just apply the exponential function, sum them all up, divide by the sum. So that's 0 as well. Surprisingly, I thought it was surprising, people did better on the convolution weights than on the fully connected layer weights. So let's talk about the convolutions. In the first convolution, how many convolutions do we have? 64. So we have 64 different kernels, all which are learning different things. So each of them has a 3x3, and we've got, convolution 1 all the way to convolution 64. So it's 3x3 actually by 3, right? So 3 by 3 by 3 by 64. If we have 27 weights for this convolution. But we actually don't have 27 weights. We have 28 weights because we add a bias. Like almost everyone got the biases here, which is great. So 3 by 3 by 3 plus 1 times 64. Right? The next one, and notice there's nothing that has to do with the size of the input here. We're agnostic to the size of the input when we're determining what the weights are. Because the weights are just for this little window that we're using to move through the image. And we'll just move through the image more if we need to, creating a bigger output. But the weights stay the same. The pattern of this is always the same. 3 by 3 by the depth. How do we know the depth? That's the depth here. How do we know the depth here? That's the depth of the output from the previous layer. Okay, so the first convolution outputs at 224 by 224 by 64. 64 because we have 64 kernels. That input then goes into the new kernels that are 3 by 3 by 64. So the number of weights we have for every kernel is 3 by 3 by 64 plus 1 for the bias. How many of them do we have? This one, we have 128 of them. So we end up with that number. And then we just keep moving down, doing that same computation. Okay? Ending up with layers of millions of weights. Right? 3 layers with a couple million weights. And then we get to the fully connected layer. So we've got this max pool that's 7 by 7 by 512. So how many outputs is that? About 50 by 512, so around 25,000. Is that right? So our fully connected layer, our first fully connected layer, has 50,000 outputs, right? 7 by 7 by, what was it, 512? Yeah. So 25. Is that right? Is that correct? All right. And this is going to, right, fully connected, the size of this layer is 4096. So we've got basically 4096. So let's not say approximately. Let's say it's equal. Total number of weights is 7 by 7 by 512. Times 4096. Okay? Except it's not quite right. The bias. How many biases do we have? Some people thought, I need to put in a bias. Most people said, I know I need biases for convolutions, but I don't need no stinking biases here in fully connected layers, and so didn't bother to put them. Some people said, bias. I'll put a +1 at the end. But that's not what we have, right? We have, for this particular output here, right, we're getting this as a, XW plus B, one particular column in that. This has a different bias from this bias, 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 right? Every one of these is going to have a bias added to it. So let me just look at this a second. Let's look at the sizes of these, because I think I actually have that wrong. So X is of what shape? Coming into our fully connected layer. Let's flatten it, actually. So it's 7 by 7 by 512. But let's just flatten that into 1 by 25K. Right? What's W look like? What's its shape? Remembering that we're going to do a Z equals WX plus B. So yeah, it's got to be 25K by 4096. And so WX, the shape of WX is we multiply this by this, and we get a 1 by 4096, right? So if WX has this shape, what shape does B have? Better be the same, right? So this is 1 by 4096. So I made an error here. I'll go back and look to see if anyone got this correct that I got wrong. This shouldn't be 7 by 7 by 512 plus 1 times 4096. Oh wait, it should be exactly that. Right, we have 4096 more biases that we hadn't counted yet. Perfectly correct, and I have no doubt about it. Questions on this? So that's adding the biases. The next one, 4096 by 4096. So basically we need to have an extra 4096 for the biases, and again 4096 by 1,000, and we have extra 1,000 for the biases. So we can see we have here, just in the bottom 3 layers, like around 120 million weights in that fully connected layer, fully connected layers, out of about 132 million. So like 93% of them are all just in the fully connected layers, which shows how those shared weights on the convolutions really can reduce the number of weights. Questions on this? Yes?
So are we trying to minimize the number of weights in this case?
Are we trying to minimize them? Well, I guess yes. So let's say we didn't use convolutions. We went through those previous layers as fully connected layers, where we were trying to sort of learn patterns. We weren't trying to have a single set of weights that was learning patterns spatially independent. We were trying to learn them separately. There would be a huge number of weights, and there would be a lot of power, and that would make it hard to train. Right? We'd easily overtrain or overfit. But it also just shows you can't throw in too many fully connected layers at the end, or you add a lot of potential for overfitting just there. More modern architectures don't have this many layers of fully connected layers at the end. They'll just use kind of convolutions all the way through, and then maybe one fully connected layer at the end. Okay? So this is about a 6-year-old architecture. And we'll be talking more about these architectures on Wednesday, different ones. Any other questions? All right, I'm going to hold off on the quiz until the end. So I'll give you 5 to 10 minutes at the end. What I wanted to talk about now, one request for your homeworks. When you scan them, can you please scan them in grayscale or color? Sometimes I have a couple people when they scan, it's I think in black and white, and it's just very hard to read sometimes. So maybe one thing you do is look at the scan before you submit it and make sure it looks like it's easy to read for old eyes, like mine. Oh, and as far as the assignment, I took just a very brief look at a couple of the assignments. I saw some surprisingly good mean absolute errors, like 18,000, 16,000. So who had it like in that range? All right, what did you do for that? Did you carefully choose like learning rates and alpha and betas?
I made the learning rate really high, and then I made beta really high also, so that I wouldn't overshoot or something. And then I also used mini batches. I changed the batch size to 25.
I see. So a combination of batch size and, screwing with the hyperparameters. That's what this is all about.
You
Josh.
mentioned that one of the things you're going to be graded on is logging everything. Should we log every change we make? Because I made all sorts of changes throughout the many hours of working on the project, and I don't know how to log it in a clear and efficient way. If that makes sense. Do you have any?
Every single change is not necessary, but some general ideas of approach. I don't need to know every value of every hyperparameter used. But the fact that you were trying changing the learning rate, for example, I want to know if you change the optimizer. That's something I would want to know. And if you just wanted to spend 4 hours screwing around with the learning rate, very frustrated, you could. That would be sufficient for that part of it. Other questions? All right. So I want to look at a notebook for training dogs versus cats. Okay, so learning how to distinguish dogs versus cats. And we're going to look at let's see. Let me just bring that up a second. All right, so this is, and by the way, I figured out how to do dark mode in Colab, and I'm very happy because it works a lot well in the video, a lot better in the video. Okay, so this is part of the Toilette book again, and this is training a convolutional neural net on a small data set. When you're using a small data set, what you're worried about is what? Overfitting. Yeah. If you have a large data set, let's look at a large data set. Let's look at like ImageNet. So ImageNet is a data set of, I believe it's 1.2 million images in 1,000 categories. Right. And this was used as a competition for many years, about a span of about 5 years, I guess, and really helped improve the state of the art and created a lot of new architectures for image recognition that we'll be talking about. How did they get 1.2 million labeled images? They did not have a grad student out there that took 1.2 million photos and logged for each one what it was.
Didn't just pull them from Google Images and then classify them?
They pulled them from the net, basically. Yeah, from the internet. Okay, so we could probably figure out how to scrape 1.2 million images, but then how would we label them?
Are you also going to do data augmentation on these?
No data augmentation in these images. Now, today we'll be talking about data augmentation as a way to address having a small amount of data. But if you have a large amount of data, you don't necessarily need data augmentation yet.
Mechanical Turks.
Mechanical Turk. They were like the largest user, at least academically, of Mechanical Turk for 1 or 2 years back in the early 2010s. The Turker, they're called Turkers, aren't they? I think they're called Turkers. Anyway, the people who do this, who get paid the small bucks, I think would do like something like 4 or 5 images a minute, something like that they would identify, which is harder than it sounds because there are 1,000 categories. So you need to perhaps distinguish between a Basset Hound and a Springer Terrier or whatever there might be. There are several dog breeds in there. Right. But anyway, there is this large amount of data. We're not going to be doing training with 1.2 million images because it would take us forever, and we would use all of our collab time, and we would not be patient enough to wait. So we've got 4,000 pictures of cats and dogs. 2,000 that we're going to use for training, 1,000 for validation, and 1,000 for testing. And let's just look at how we might set up a convnet. So aren't those cute pictures? Some are dogs, and some are cats. The notebooks that are in the book are unfortunately not very useful because they don't provide the data or any way to get the data. So these notebooks have been modified so that they actually will get the data. So I threw the data onto GitHub, and we basically go through, and if we haven't already got a directory called dataset cats and dogs small, then we go ahead and do a git clone and pull it out. Why this test to make sure it doesn't exist? Tell you why. I always do a run all, or I very often will do a reset and run all. And so if I'm going to run all, I don't want to reload my data again and again and again. So if the data was already pulled down into this instance of Colab, it just goes there. I don't have to rerun it, and it's quicker that way. That's what I recommend. I recommend you have a notebook that you can easily run from top to bottom, and if you run it again from top to bottom, it's not going to do unnecessary stuff. Okay, so it's got these different images. We're going to create a network. We're going to have, so we have here the 32 means, 32 kernels of size. 3 by 3, using a ReLU, taking a 150 by 150 input. We had some max pooling, another convolution, convolution, max pooling, convolution, max pooling, flatten. And then we have a 512, and then I can't see the rest of it, unfortunately. But actually, let's just look at it here. So we have one fully connected layer with 512 and then down to 1. Right? Where our 1, what's our activation function going to be for this? Would we guess? Sigmoid, because we want to know, what's the probability it's a dog? Okay, we'll interpret that as a probability. So sigmoid gives us a nice number there. So very small network, we only have 3.5 million weights. 3.5 million weights, 2,000 images. We do have to worry about overfitting for sure. We are not normalizing our data. So we're scaling it to be between 0 and 1, but we're not doing any normalization for means and standard deviations. Sometimes that is done for this sort of processing, where you basically normalize each red, green, and blue channel independently. This is going to be of use to you, this image data generator. So image data generator will do some augmentation of your data. This is the simplest thing it can do, is just rescale it. And that's all we're going to do to begin with. We're going to do some more in a bit. And then you can tell one of these generators to flow from a directory. That is, to take data from a particular directory. And then it assumes this directory is going to have, so this is our directory. It's going to have category 1, category 2, to category K. How many categories do we have for this problem? 2, dogs and cats. So in our case, this might be, let's say, the validation directory, and we'd have cats and dogs. And then within each category, we have our sample 1 all the way to sample J, let's say, for however many samples we have. In our case, how many cats do we have in our validation? I have to remember the numbers. We have 4,000 total. Half of them we use for training, and the other half we split between validation and test. So we have 1,000 total test samples. So we have 500 images here and 500 images here for validation. Test looks the same. Training, we double the numbers. Does that make sense? So this flow from directory assumes this format. Okay, it doesn't actually care what these names are, just that they're unique and that it's the same names from test to training to validation. When you are flowing from directory, you can ask it to resize. So this target size will resize it to fit this size. So we've designed our convolutional neural network to take it in 150 by 150. So that's what we make sure we get here, even if our underlying images are of a different size. We specify the batch size. So what will happen is, this is a little odd, this generator is going to basically spit out batches of 20 at a time. Okay. So when we ask the generator, it's an iterator basically. You say next, it gives you a pair of X and Y, each of which is 20 big. And the Y's, in this case, are going to be binary, either 0 or 1. If we had more classes, and this was a categorical problem, we'd say categorical here, and then we get these 1 hot Y's. Okay? But binary just says the Y is either 0 or it's 1, as we'd expect for this for this problem. So we don't have any output there. That's too bad. We've seen the fit function, right, of a model. There's also a fit generator that takes one of these generators instead of actual X's and Y's. So, we give it a train generator. This is a little funky as far as I know. So we have the number of epochs, and then we have the steps per epoch. Okay? The generator is going to give us a batch, because remember I told you you specify your batch in your generator. So it's going to give us out, I think I said 20 at a time. And this says 100 of them makes up an epoch. So 20 times 100 is 2,000, which is the 1,000 cats and the 1,000 dogs in our training. And then we can also produce validation in the standard way, so it can compute validation accuracies, validation metrics. So if we run this, we get some validation accuracies of around 70-odd%. Okay? And we can see a chart that seems to show what phenomenon? Overfitting, right? You look at the loss, it goes down, kind of stays about the same, and then starts going up. So we should have stopped there. And 78%, I mean 50% would be random guessing, so it's better than random guessing, which is always a good thing to attempt. As I was doing your next assignment over the weekend, I spent hours and hours and hours getting basically random accuracy on my validation over and over and over again, which was quite frustrating. So what can we do? One thing we can do is augmentation. Right? We've talked about augmentation back probably on the first couple lectures. I think we talked about that. And so the image data generator will do that. The image data generator will do rotation. So this is in degrees. It will scale the width or the height. It will do zooming, so zooming in. The shearing, do you guys know what shearing is? This is, yeah, like if you had something like this, shearing it's kind of like that. Okay, so it shears it, I guess you'd say. Horizontal flip, there's also a vertical flip. For dogs and cats, does a horizontal flip make sense? As augmentation. So if you see are cats always facing to the left? Sometimes they face to the right. Okay? However, what about vertical flip? Would that make sense? So dogs kind of stand on their 4 feet often, right? Do you often see them with 4 feet up in the air? I mean, my dog sometimes, but it's not that common. Okay. By the way, are you familiar with the anti-gravity device? So basically, take a piece of buttered toast and tape it to the back of a cat, right? Because buttered toast always falls butter side down, but cats always land feet down. So it's a weird quantum effect. All right, so, and then fill mode is for some of these, you're going to end up with empty pixels. And so what should you fill it with? Fill it with white, fill it with whatever was nearest it, something like that. And so if we do this, we get all sorts of different possibilities. So we have this same picture, which has been augmented in a variety of different ways. So we have some flipping, we have some zooming. I'm not sure whether there's shearing. Oh, it's kind of a weird looking cat. Okay. So we're going to go ahead and modify our neural net. So we are going to be doing data augmentation, which will reduce overfitting. We're also modifying the neural net. So this part looks the same, 150 by 150 by 3. We still do 2, 3, 4 levels of convolutions. I think that's what we did before. We did a flatten. We did a dense 512. We did a dense 1, and we've got this new thing, which is dropout. So dropout is a form of regularization, which I've not yet mentioned. So if you remember, back when we were talking about regularization, we were still back in polynomial land for our regularization, and dropout really doesn't have any parallel with polynomials. So this is a form of regularization called dropout. Here's the idea. Randomness can help in preventing overfitting. Here's what we're going to randomly do. We're going to randomly drop nodes. That is, if we have a neural network, right, and we have all these connections, and we have all these connections here. We might say, let's just say this node isn't here. Okay? And that will impose a new network. So if we get rid of this node, that node will go away. And effectively, so will the incoming weights and the outgoing weights. Right? So this is a stripped down network. And here's what we're going to do. For every batch, well, actually, let me first show you how we're going to implement this. Okay, the way we're going to implement it is we're going to actually add a layer here. So I'm going to get rid of those colors there, and I'm going to put this one back, and I'm going to have a special dropout layer whose job is only to implement this dropping out nodes. So the dropout layer is here. And the dropout layer has its inputs coming in and then has outputs going out as they would normally to the next layer. So right. And there's basically, think of it as a little switch in here that'll get turned on and off, probabilistically and independently. But in order to implement turning off this node, basically what we'll do is we'll just turn that off. And we will feed this out as if it's a 0 coming out of here. So the other ones will stay the same. This one will come out as a 0. Does the idea make sense? So on every batch, in our dropout layer, drop each node with probability p. That's our dropout probability. And then do the forward pass and do backwards prop. And then restore it once we're done with this mini batch. So just for the time that we're running this mini batch, we drop some number of these, flipping our coins independently. In this case, our coin said this is our winner. None of the others happen to be winners. We drop this one. We do our forward pass, which means the output from here is going to be completely ignored. We do our backward pass. It means these weights are not going to get updated that go into here, and these weight back is not going to get updated. And then we restore it. And then do our next mini batch. Our next mini batch could have different settings for these, right? It probabilistic will choose different ones. So it's as if we're creating multiple networks, each having some of them dropped out. Right? There's 2 to the k different possible networks if there are k elements here. We do have a lot of mini batches. We're probably not even close to approaching 2 to the k. But we come up with this ensemble of different networks. each with a certain amount of memory loss.
Is this something that's most often seen in convolution neural nets, or like I guess why bring it up now, not before? Like, is it something we would use, or we could use? In our
Any neural network, we could do this. And actually, it's not normally convolutional networks. No, we could see this anywhere. So it's a very common regularization technique. So the deal, though, is we don't actually create multiple networks. We share exactly the same weights. So we do this and update our single set of weights. And then we do another mini batch and update our single set of weights. And another mini batch and update our single set of weights. And we just use our final set of weights as our final learned network. And we allow all of the neurons to work when we're doing prediction. So this is only during training time. All right. At prediction time, we do one thing. And by prediction time, I also sometimes might use the term inference time. Right? If we're checking our validation loss or our training loss, we again would just be doing a forward pass without any of dropout. The only thing we do is we adjust for the fact that the magnitude of the inputs coming in here when we were doing training is going to be different from the magnitude now that we've turned off our dropout. As an example, let's say we have an extremely high dropout. So dropout P equals 0.9. That's very high. This often might be 0.1 to 0.5. Okay? That is, we drop out 10 to 50% of the nodes in a particular layer. And we could have multiple dropout layers at different parts of the network. If we had a very deep network, that's certainly possible. But let's say dropout is 0.9. So every time we're training, we get rid of 90% of the inputs. The total weight coming into one of these, let's say, has some average value. If we now turn on all of these, this value is going to be a lot bigger, right? It'd be like 10 times as big. So we did all this training, getting the magnitude of this within a certain range, and now it's going to be 10 times as big. So what we normally do at inference time is rescale the outputs. We want to make them smaller or bigger? All right, give me an argument for smaller and give me an argument for bigger. Smaller, go.
I thought it was going to be bigger, since you wanted to match what it would have been without dropping things out.
Okay. Does that work for you?
Yeah.
Okay, good argument. So we want to make it bigger. And in fact, we want to make it bigger by 10 times. So basically, if we had an output, we want to make it an output times, what would this be? 1 over 1 minus b? I just have to test one value, and if that works, I know it'll always work, right? So 0.9 is 1 over 0.1, which is 10, so we're scaling it by a factor of 10. Okay. That's dropout. The scaling, we don't have really a great mathematical proof of why that would work. In practice, this works pretty well. Okay. Questions on dropout? Yes?
In Keras, does it rescale the output automatically? Or
Yes, it does.
It does.
Yeah. In fact, let's just take a quick look. Keras. let me type. It's often very useful to just look at the source code. So Keras, source code, dropout. I don't want it explained. We don't need no explanations. We just want to look at the code, right? So here's dropout. Let's just take a look. The noise shape, I think, is the idea of whether it's sort of zeros and ones mask. I think that's going to be applied. Call. So we get a noise shape. That is, figure out what's going to be zeros and what's going to be one. This tells us what's dropped. And if we're in the training phase, we drop them. Okay? And then it'd be really handy to see what the scaling, where the scaling is. And I don't see the scaling here if we're not in the training phase. And it might be that Keras does it the other way around. So the other way you can do it is, rather than rescaling the outputs at prediction time, rescale them at training time. So instead of making them how did you live? Let's get back to this. We got to look at this. I went well on with you guys. So we make it bigger here. Why would we make it bigger, the prediction time? Say your answer again. That's right.
That will match what it should have been without dropout layer.
So at training time, we have a dropout layer, right? And what happens to these outputs?
Cut down.
They're cut down. At test time, at prediction time, they're all there. So what happens to the outputs?
They are still cut down. Yeah.
So if I am getting rid of 3 out of 4 of these during training time, then these outputs are going to be smaller, right?
Yeah.
At test time, they're going to be 4 times bigger if I have 4. So at test time, I don't want to increase them because they're already increased.
Right.
I want to decrease them. I don't know how you were so convincing earlier. We need smaller. Okay, so therefore, we want 1/10 as big times 1 minus p, not times 1 over 1 minus p. Does that make sense? Because as we're training it, we get small amounts out of that layer, and all of a sudden, as we go to test time, we say, open the gates, open the floodgates, and let them all come forward, and now it's going to be much, much bigger. So we need to scale it down. We could scale here. The other thing we could do is we could scale here. We could make them bigger here by the right proportion, so that once we unflood them all, we don't scale, and we get the same effect. Yeah.
Is test time the same as prediction time?
Test time the same as prediction time. We'll also call it test. Yeah. All right. So adding dropout. And so I would have to look at the code for this. My guess is if I look carefully, it's actually doing scaling at training time. One advantage of doing scaling at training time is, let's say you wanted to have a dropout that changed as you were training. So you might start high and go low, or start low and go high. Well, you can't really deal with a single amount of scaling at prediction time, but you could be modifying the scaling that you're doing here over time so that the total amount of output, the rough magnitude, continues to stay the same, even as you change the dropout percentage. So by adding the combination of dropout and data augmentation, we should get, that was before all that. We get a better value. So we're already up into the 80s. Right? And we can see here that validation loss seems to still be going on a downward trend. Maybe at the end it's going up. It's kind of hard to tell. Okay? Does that make sense? So drop out, a new arsenal to add to our regularization techniques. In practice, if we need to be learning something about images, we don't want to start from scratch. We want to do some transfer learning. We want to take advantage of a neural model that's already been trained on, let's say, 1.2 million images with all these 1,000 labels and use that. So your homework was an architecture called VGG, I believe it was 16. 16 is the depth of the network, right? So it came in, it did a convolution, it did ReLU, it did a max pool, it did some other stuff, and then it does a fully connected layer, and a fully connected layer. This is what, 4096, 4096, and then the final output was how big? 1,000, because there are 1,000 categories in the ImageNet. Okay. So this part, I'm going to call the base. This is the convolutional part. What's coming out of the base is what? This 7 by 7 by, how big was it? 512? 512? Right, so if we look at that, we had 512 of these, right? What does any particular row and column in here represent? Santi?
Some sort of feature extracted from the network.
Some sort of feature in this general area, right? So this particular feature, if we're at the very end of our convolutional network, would this be a low-level feature or a high-level feature?
Very high.
Yeah, this would be very high level. Now, it might not have a meaningful name for us, right? But it might be, this might be an eye detector. And there's an eye kind of over here and an eye over here. Useful if you're identifying cats and dogs. Although since they both have two eyes, it's not clear how that would be useful. But perhaps one is pointy ears, right? That might be useful. Or we have another one, or another one, or another one. All sorts of different features, whatever the network has come up with. And these fully connected layers just put together these features in various ways, so that we can identify these 1,000 categories. But there's lots of good stuff in here and lots of features that have been learned. There might be whisker type things, fur type things, colors of various sorts. What else might distinguish? Well, sorry, it's all these 1,000 different categories. So it includes probably buses. So there might be things that identify wheels and stop signs and all sorts of stuff. But among them is stuff that's probably useful with cats and dogs. Especially because more than one of these 1,000 categories is actually particular kinds of dogs. So we actually know it works for dogs, but it will work for other things as well. So we want to reuse this. We want to reuse not just the network, but the trained weights. So we're going to take advantage of someone having trained this VGG for in the past weeks on a GPU with all these 1.2 million images that it probably did data augmentation on, and carefully pulled hair out to figure out what would be a good learning rate, and what would be good beta, and what would be good alpha, and all these sorts of things, right? Set all these hyperparameters, and then we end up with our weights. And we're going to say, good, give me the weights. I want to use those. Because if you give me those weights, I can feed in any image, and I can get out this 7 by 7 by 512 set of high-level features that I bet would be useful for like distinguishing cats and dogs. Does that concept make sense? We're going to call this transfer learning. So we are transferring information from this other classification problem to our problem.
Does that mean that our network will have the exact same structure as that one as well?
This part will have the same structure. Clearly in our output, if we're still trying to distinguish cats and dogs, we're not having 1,000 outputs, we're having
2.
one.
Or 1.
Yeah, one because it's binary. Yeah. So this part at the end is going to be sort of custom, what we do here. But this part we're going to keep. There are a couple ways we can use this network. I'm going to show you one way. And this one we decided is around 25K, right? So I'm going to assume we flatten this at the end. So what comes out of here with a flatten is 1 by 25K features. So here's what we're going to do. We have 2,000 images, right? We're going to take our 2,000 images and one by one feed them into here. So we're going to feed into here something, how big is this? Actually, you know exactly how big it is because you guys just did homework on it. So what was the input? 224 by 224 by 3, right? So 224 by 224 by 3. We feed it in, so this is how big? This is 2, 4, 6, so it's second, fourth, fifth. So this is around 1 times 10 to the fifth, I think. So 100K? Am I right here? Is the right order of magnitude? Okay, so we're going to take this. First, we're going to get the weights. Keras, thank goodness, has a routine that will just load a VGG network and say include the weights for ImageNet. We're going to feed it in here, and we're going to come out with a 1 by 25K. So we're compressing, in some sense, our image. We're compressing it from a bunch of pixels into a bunch of features. We're going to do that for every one of our 2,000 training examples. So basically, we have x, y, right, which are training examples, and we're going to convert this into x prime y, where x prime equals sort of this VGG of x. So this one is 224 by 224 by 3, and this one is 1 by 25K. Does that make sense? And then we're going to build ourselves a fully connected network. Our fully connected network is going to have what size input? How many of these training examples do we have? 2,000. Right? We started with 2,000 training examples like this. We converted them to 2,000 training examples like this. And then we're going to go ahead and feed into our network. So we're going to have a 25K layer. And that's going to feed into, I don't know how big, 1024, let's say. Feed into another 1024. This is fully connected, this is fully connected, and this can feed into, let's say, a 1. So we are taking a layer, a network that takes in features as constructed by the VGG on the ImageNet and produces, is it a cat or is it a dog? How do we initialize all these weights? How do we initialize all of these weights? We download the weights. We download the pre-trained weights. Okay? We run these down, run them through, all 2,000 of them, and then we're going to use those 2,000 and we're going to run a bunch of epochs. Yes?
Yeah, so for the, you're saying we initialize the pre-trained weights, are we then training those weights more or just keeping them?
We're just using this network as a predictor. We're not doing any training on these. We'll get to that idea maybe of like fine-tuning this, but for now we do nothing to this. We just run it as is. And then we get these outputs, and we have these 2,000 training instances. And we train. These get initialized too. How do we normally initialize our weights? Random. So these are they start random. This is going to train much quicker than, back up a second. Having only a 3-layer network trains quickly. So this will train quickly. We're going to run a bunch of epochs. So we're going to be running through these training instances multiple times. Right? If we do 100 epochs, every training instance we're going to go through 100 times. We only have to run through this once per image. Right? And then we just keep replaying them over and over again.
We do have more than 2 classes. How are we going to modify this thing to make sure this still works?
If we had more than 2 classes, like if it was cats, dogs, and rats, we would have 3 outputs, and we'd use a softmax. That's the only change we'd make.
Are we going to use a different loss function?
Yeah, we would use categorical cross entropy for the softmax and binary cross entropy for the binary case. So yeah, there is that slight difference as well. Does this make sense?
So, in what cases would we decide to use transfer learning opposed to build from scratch? Like, is VGG 16 just something that's used all over the place? And like,
there are a bunch of different architectures. VGG 16 is an old one. There are a bunch of others. ResNet, Inception, Exception. We're going to talk about all these in the next couple of days. And you use whatever one strikes your fancy. Okay. I guess VGG has an example, has an advantage, is in it's a relatively small network. And so you can run through this base part relatively quickly. Does that answer the question? Basically, if you're doing anything with images, you use one of these pre-chain networks because there's no reason to start from scratch.
or would there never be a reason to start?
Well, if you're building your own type of network, yes. If you're out there in practice trying to distinguish things, you use a pre-trained network and you tweak it. Okay? But if you're trying to, if your goal is to build something from scratch, then you build from scratch. But there's going to be a lot more training. Any questions on this concept? So, in the previous case where we had our custom network that we created ourselves, how did we get rid of overfitting? Or how did we reduce overfitting?
You could slip our model and reduce.
No, how did we do it? When we just went through it and looked at it. What were the two techniques we used to try and reduce overfitting? Dropout and?
Sort of just.
Dropout was one of the ways we did it. And there was another thing we did. Data augmentation. Okay? We could throw some dropout in here, no problem. That'd be fine. But we can't do data augmentation in the same way I just talked about. We can't one time run our 2,000 training instances through this. Because to do data augmentation, we need to work in this level here, right? So we need to go ahead and augment here. And for every single image, for every single epoch, we need to run it through the base convolution layer. And then through this. So we will continue with that on Wednesday, yes?
Wait, does augmentation happen once or once per epoch?
The augmentation happens once per epoch.
So you're actually augmenting every epoch.
Every epoch, yeah, you're going through. And so basically what happens, at least with the Keras one, I believe, is it's actually the way the Keras one works is you give it a directory, right, with a bunch of things in it, and it will just pick an image, augment it according to the random parameters the way you set it, do another, and just continue forever, infinitely. So that's why in fit generator we actually have to say, like, how many steps per epoch? How many times do I want to keep calling this?
How much more data do we usually get by using the data augmentation function?
Commonly, since you get a newly augmented one per epoch, it's the number of epochs you have. So if you have 50 epochs, you have 50 times the number of training samples. Now, they're still correlated with the originals, so they're not as good as brand new examples, but still pretty good.
How would that look in like this example where you do this before you like run through?
I'm gonna leave that open. I'm gonna tell you, the hint is what we're gonna do is instead of running this network and then turning around and running this network, we're gonna smash these two together. And we're gonna say, we take off the old head that we don't like, and we're gonna smash on a new head and then freeze this stuff so it doesn't change while we're training. And then update it. Yes, Anton?
Did you have the results of this?
Yeah. It would be impressive if we're better, right? So, just to use here, notice VGG16, and we say the weights are the ImageNet weights. And we extract the features, which means basically we just save those 2,000 into these training features, validation features, and test features, and then we create this fairly simple, in fact, it's just a 256, right? So we're feeding those 25K into 256, the 256 into 1 with a bit of dropout. And what do we get? We're now in the 90s, okay? And each epoch takes just a couple seconds because it's a small network. All right, so what are we doing on Wednesday? We're going to look at data augmentation. We're going to look at patching these two together into one big network that we'll be doing training on. All right, quiz.